Hello again, my lovely students. So we are now moving into chapter 3. Chapter 3 has to do with graphing functions. Specifically, graphing trig functions sine and cosine. So the beginning of the notes is just kind of talking about the graphs, and then there's a whole bunch of examples for all you have to do when you're figuring out how to graph them. And the way I cover it is different from the way the book covers it, so pay attention. The end result is the same. It's just, well, yeah. All right. So if we just pull the sine values from the unit circle starting at 0, pi over 6, pi over 4, pi over 3, pi over 2, those are, sine starts at 0, goes up to 1, comes back down to 0. If we look at 3 pi over 2, sine is at -1, and then at 2 pi, it's back to where it started at 0. So our graph here is showing us the same thing. So that is one period of sine. So after 2 pi, we're back at the start on the unit circle. So 2 pi to 4 pi is going to do the same sine values. 4 pi to 6 pi will do the same sine values. We go backwards. 0 to -2 pi, we'll go through the values backwards. So it'll continue down and then up in that direction. So the 5 points I highlighted here are the 5 key points we're going to focus on when we're graphing the sine graph everywhere. So we've got the high point, the low point, and the 3 points in the middle that form what we call the midline of the graph. Now we can also see here, if we look on the unit circle, I draw the unit circle next to this graph, this point here maps there, here, here, and so on. And then I take these over here, they're going to map on this arc, etc. Now I can do the same with cosine, but notice cosine starts at 1 and then goes down to 0, down to -1, and then it'll come back up to 0 and then finish back at +1 again. So if we look at our graph here, it's going to be the same angle measure position, but the points themselves are in slightly different spots. So still 0 degrees or 0 radians, pi over 2 radians, pi radians, 3 pi over 2, and 2 pi. And those are our cardinal directions on the unit circle. Now we talked a little bit about this in a previous section, 2.3, I think, but what it means to be an odd function. Odd functions are symmetric about the origin. This is the graph of the sine function extended further. So let me just highlight this one's sine. So you can see here it starts at 0, 0. It goes up to pi over 2, 1, and it goes down to -pi over 2 and -1. So everywhere there's a point on the right, I will find a matching but negative point on the left. Cosine is an even function, so it's symmetric across the y-axis. And so when we look, if I cut the graph right there on the y-axis, I can fold those two sides up and all the points will line up perfectly. So sine of a positive x will be the same as sine of a negative x. All right. These are periodic functions. They repeat every 2 pi, and it's because 2 pi is on the unit circle. Their domain is all real numbers. I can put any value I want into a sine or a cosine function. And my output will always be between -1 and 1 inclusive. And we saw in the unit circle the lowest value, the highest value, that those ranged. And then it just renumerates the symmetries there. All right, so if you stretch your brain, you took 1073 or when you last took algebra, They should have talked about the transformation of functions and all the different letters we can apply to a function to change its shape. Now, up until now, every graph we've had that we've applied a vertical stretch to, there was also a number that we could have applied as a horizontal squash that would accomplish the exact same thing. And that was because there was a way to move numbers inside a function to outside a function. Like there was some way to make meaning with that. So there's some way to write horizontal and vertical stretching the same way. Trig functions won't let you do that. There is no nice way to take a number out of a trig function. Like sine doesn't distribute across multiplication or addition, neither does cosine. They do their own special brand of weird things. So this means a horizontal stretch is going to be different from a vertical stretch. So think of it like a slinky. So if I squash a slinky, like it goes faster, but I'm not making the slinky wider. If I stretch a slinky vertically, now I've made a bigger circle. So as long as I didn't compress it or stretch it horizontally, it's going to go the same frequency. It just won't go as high and as low. So those two things are distinct. All right, so if we ignore horizontal and vertical shifting, we have this graph A of sine A times sine of bx, A times sine of cosine bx. The period is 2 pi over b. So the b number here, the stretch number, works backwards from what we would expect. Like I see the sine of 2x, I would expect the period to be 2 times as large, but instead it's half as large. And we're going to see this more in examples, but there's one of our things to remember. And then you look here at these examples, all right? So our normal graph is the orange. That's sine of x. Sine of 2x is twice as fast as sine of x. So if you think of that number as a frequency number, higher frequency, the graph goes more rapidly back and forth. That kind of jives with our gut sense. But it's not multiplying the x values by 2, it's actually dividing them by 2 so they happen faster. When we look at sine of x over 2, it only goes through half of its period from 0 to 2 pi, meaning it'll take another 2 pi all the way up to 4 pi to get that full period. So it's kind of weird because we've got this like dual thing going on. What does it do to x values? It's backwards. What does it do to the graph? It makes it more frequent. Okay, so our first try it here is determine the period of the function. So we need to identify our b value. So cosine of x over 3 can be written as the cosine of 1/3 x. So that 1/3 is our b. And then our period is 2 pi over, and they wrote the absolute value of b just because if we get a negative on the b, it means something a little bit different. It means a reflection, but just the size of the b value. So dividing by a fraction is the same as multiplying by the reciprocal. So the period of cosine x over 3 is 6 pi. So this graph is 3 times as long as our regular cosine graph. So that's a horizontal stretching and squashing. Down here, we've got a picture of graphs with different amplitudes. Now I want you to look, the period on each of these is the same. It takes 0 to 2 pi to get a full up and down cycle. But the how high and how low it goes is what changes when we change that number multiplied to the front outside of the trig function. So we often refer to that letter, it's A in the formula, and I think of it as A stands for amplitude. And that's what we call the distance from the midline to the high point or the midline to the low point. Those two distances are the same, and that height is called the amplitude. And that's what this formula here is talking about. Half the maximum value minus the minimum value. So if you're looking at a graph and you're trying to figure out what A value would produce waves this high and this low, you do the high minus the low and then do half, because that high minus low is going to be the measurement for two amplitudes, the positive, the one above the midline, and the one below the midline. Okay, so the amplitude of this guy is the absolute value of the number in front of sine x. So A for amplitude is absolute value of -4, which is 4. What is this 4 going to do to the graph? The 4 is going to stretch the graph so it's 4 times as tall. The negative sign will cause the graph to flip. And in this case, a negative on the outside is taking positive y's and making them negative, taking negative y's and making them positive. So it's flipping across the x-axis. So it'll be stretched, it's not compressed. Our outside numbers, what we see is what we get. So we got times 4, it's 4 times as tall. Times 4 on the inside, it's squashed by factor 4. It's 4 times as fast. All right, now our horizontal and vertical translations. So horizontal translations, we saw these when we did parabolas, not necessarily we, but when you do parabolas, we have the h and the k as the vertex. That h and that k are actually the horizontal and the vertical translation of the parabola. So here we've got the formulas again with the same h, and hopefully you remember that these were backwards. So when it was minus a number, it went to the right. When it was plus a number, it went to the left. So this happens backwards what you see. You might see f of x plus 2 and you think, oh, that's going to go 2 units to the right. No, that is inside the function, so it lies. So it's actually going to go 2 units to the left. And that's what this whole paragraph talks about. All right, so if we look at our graph here, they've actually shown us a couple examples with some horizontal translations. So sine of x minus pi over 4 has taken the graph of sine x in dark blue and shifted it over. So instead of the 0 starting on 0, it's starting on pi over 4. Then our high point will be halfway between pi over 2 and pi, which is 3 pi over 4. The 0 point here of 5 pi over 4. Orange graph. The low point at 7. That's our 5 pi over 4. That's our 7 pi over 4. That's our 9 pi over 4 for our full complete. That's for a little more than a sine graph. All right. Sine of x minus pi actually takes the sine graph, and if I drag it over pi, it'll line up. But if I flip it across the x-axis, I'll also get the same thing. So we can't actually reason through some strange equivalencies based on the way the graphs work. and exploiting the fact that periods are repeated. So our last type of transformation is a vertical shift. So this happens when we have a value outside the function that's being added or subtracted. And if it's outside, then it's straight with us. So f of x plus k, it's going to shift the graph up k. Minus k, it's going to shift the graph minus k, or down k. All right. So the book has a very similar formula, but they write bx minus c in the parentheses. This is not wrong, but it means to figure out how far the graph gets shifted, you can't do it just with c. You end up having to do it with c over b. And that can get a little more hairy, in my opinion. If I'm already going to have to do c over b, I may as well just factor b out of the whole equation, so I see them as two separate things. And then here, instead of c and d, I went back to the h and k notation. All right, so what I have here is a long description that I put together last summer. I made a couple of tweaks, but this is the, like, you got a graph that's going to tweak everything, follow these steps. So the first thing, after we figure out what the base graph is, so we start like with all right, here's our original graph. Then the first thing we want to apply is there a horizontal stretch factor? So does this shape I have get compressed or stretched horizontally? Once we have those new points mapped out, then we'll determine if there's a negative in front of the b value to know if the whole graph is supposed to flip. And if it's negative, we flip the graph across the y-axis, which is a left-right mirror flip. All right, then we take care of the horizontal shift, h, inside the parentheses. This one lies, so we do the opposite of what we see, shift it left or right. All the points on the graph get shifted. Fourth, we apply a vertical stretch factor. So once we've got it squashed or compressed horizontally and picked up and moved around, now we apply our vertical stretch, and that's just changing our amplitude. So either staking it out higher or squashing it so it's not as tall as the original graph. We double check to see if there's a negative outside the function. This is going to be a positive y for negative y, so an up-down flip. And then the last one is checking for a vertical shift up or down. So if we try these out of order, it can mess with our head, like where the different things are supposed to occur, when they occur. So I have here a picture of what I nicknamed my Franken function, and I have labeled the order that you consider these things. So notice everything inside the function happens before everything outside the function. So when we start with our graph, we're going to figure out all the horizontal changes, then we apply the function and consider all the vertical changes. And then I have like a shortened down version with multiple steps. Okay. And then on the notes here, I yanked this graph paper from a file that we're not using yet. But it's really nice because the vertical marks are done by pi over 2s. Like the tick marks on the horizontal axis, the tick marks on the vertical axis are by 1s, but we also have the little decimals in between. Although they're a little weird because they are apparently like 5 by 5. Yeah. So 4 tick marks in there, like the halfway mark is actually halfway between 2 of the smaller tick marks. So we'll figure that out later. All right. So let's graph this one, and then I'll cut the video and go to a whole bunch of other graphs, like more sine and cosine. All right. So this says determine the direction and magnitude of the phase shift. All right, so we have x minus pi over 2. minus pi over 2 looks like left, because that's where our negative numbers are, but the inside lies. So this is going to be right. Pi over 2 units. And then the only other thing this graph has is the amplitude of 3. So if we were going to graph that, all right, let me go with a couple. So our first one is 0 up to 1 at pi over 2, back 2 pi, down to 3 pi over 2, back to 2 pi. That's sine. Rewind. We're looking at cosine. Yay for erasing. Cosine starts at 1. And if you're not sure, think about where the unit circle starts. 0 degrees is the point 1 comma 0. Cosine's the x, so cosine starts at 1. We are literally just taking all the unit circle values and graphing them. So, there's our regular cosine of x. Now our cosine of x minus pi over 2. We said that goes right pi over 2. So instead of here at 1, 0, I'm going to shift that to the right pi over 2. So now it's pi over 2, 0, or 1. And then, but I haven't squashed it. This is just pick the whole thing up and move it. So each one of these points is going to get shifted over. All right, so this guy is the cosine of x minus pi over 2. Now the 3, I'm going to take my key points. My 0 points are going to stay where they're at. The amplitude 3 times 0 is still 0. But here I'm going to multiply the y values. So at pi over 2, it's now going to be, instead of just 1, it'll be 3 times 1. So this one will zoom out a little bit. It's going to go all the way up to 3. Still goes through the 0, 0. Then here it's going to go down to 3. Then still back to the 0 point, and then way up to positive 3. So now this is 3 cosine of x minus pi over 2. Now, the funny thing is, if I extend this, so like once you have one period, you can copy it again. And so this one, it's like 2 periods. It'll go back to 0. Then it'll go down here to 3. And now when I finish the drawing, you should note that this actually looks like a sine graph. Cosine and sine are so closely tied together that one is a graph of the other, just shifted pi over 2. So some of the questions in the homework may ask, like, write me a function that satisfies this and then write me another one. And they're often meaning you have the sine, now write it in terms of cosine with that pi over 2 shift, or vice versa. All right, so that's our down and dirty, just using those key points, picking it up and moving it, and then stretching it. All right, I'm gonna stop it here, and then I'll come back for the next one.